All right, hey y'all, Mr. Kyle, Mathematics. Jump right into it. We have number 35, n to the 1 over n power, where n is greater than or equal to 3. For each of the following sequences whose nth terms are indicated, state whether the sequence is bounded and whether it is eventually monotone, increasing or decreasing. So let's look. And I like to look with a t-chart. I think a t-chart's a really good way to just take a look at the data, see what's going on, and we can just kind of like see the patterns as they happen. So I usually like to call it A. And that's what other people like to do too, so I'm not really that original, but hey, it works. So why buck the system? In A sub n. So n is starting at 3. We're going to start at 3 then, I guess. So then that would be 3 to the 1/3 power, which is the cube root of 3. And most of these numbers I am not going to know what they are, but you know, it is what it is. So 4, that would be 4 to the 1 over 4 power. That one actually we can approximate. That would be the same thing as, because that would be the 4th root of 4, and the 4th root is basically the square root and then the square root again. So the square root of 4 would be 2, and then the square root of 2 is approximately 1.4. Sorry, 1.4. I wrote 7, which is the square root of 3. Oops. So about 1.4 for that one. So that I guess we can approximate some of them, but that might be the only one actually. We'll see. 5. So 5 to the 1/5 power. 6. 6 to the 1/6 power. We're going to start actually figuring some of these out. So I'm going to pull up Desmos. And let's see, do I have this up here? Yeah, I had the 5.1 sequences. I might just pull up 5.1. This is where I'm getting it, by the way. I've mentioned this in the beginning, but this is where I'm getting them from, is from the Open Stax textbook, because it's a free textbook, which means that, you know, no matter what textbook you have access to this one as well, the 5.1. So I'm actually going to pull up Desmos if I don't already have it. I guess I don't already have it pulled up. That's weird, because I normally always have Desmos pulled up. Let's see. 3 to the 1/3 power. 3 to the parentheses 1/3. Let's see what that is. Oh, that's a weird place to put the parentheses. There we go. That's better. About 1.44. Okay. So 1.44. Let's go ahead and see what 4 to the 1/4 would be. And even to make this better, I'm actually just going to graph it. And that way I can easily plug in a bunch of different values. So I'm going to say f of x equals, you know what? Let me drag this over so you guys can see this too. I'm going to drag this over. Can you guys see this? Okay, so check this out. I'm actually gonna minimize that so I can see a little bit more of this as well. Okay, so we're gonna do this. Drag this over here. Okay, so we said it was what, x? Actually, I'm gonna pull this over here. There we go. That's better. Okay, so x to the 1 over x. Yeah, x to the 1 over x. And the reason why that's helpful is because now if I want to know what it is when it's 3, I just put f of 3. And then boom, there it is, 1.44. What about f of 4? 1.41. Okay, so I had it to within 1 decimal place, but it was really, really close on the previous one. So 1.44 versus 1.41. Okay. So then what about 5? Let's see what that would be. 5 is 1.38. Okay, now we're starting to get somewhere. 1.38. So 1.38. And let's go ahead and do 6, and then after that we're gonna do like some crazy numbers. So just to see what's happening here, 1.35. It's going down really slowly, but it is going down. 1.35. Okay, now let's do some crazy numbers. Let's start with 100, and then we'll go to 1,000. And then pause it if you want to try to calculate these, either on Desmos, or if you just want to try to guess what's going to happen. See if you know 1,000 to the 1 over 1,000, and what those are going to be approximately. Okay, I'm going to go ahead and pull these up, and let's see. So 100, 1.05, that's if I'm still rounding to 2 decimal places. So 1.05 And then let's try 1,000. So 1,000. Yeah, at that point, well, no, it would still round to two decimal places. That would still be 1.01, but we are just barely something other than 1 at that point. It is going down to 1 really, really slowly. That would actually be 1.01. So with two decimal places, we're still getting something a little more than 1, even at a sub 1,000, which is actually really slow. I mean, if you do this with a lot of different sequences, normally they decrease to whatever they're leveling off at pretty quickly, but this one, it's taking a while. And that's just the nature of the way the function works. But if you think about it, it's like, okay, so n is increasing, the base n, uh, which, if you have a bigger base, then when you take it to the same power, it would be getting a lot bigger. Like, 2 to the third power is only 8, but 3 to the third power is 27, 4 to the third power is 64, 5 to the third power is 125, and so on and so on. So if the base increases, assuming the power doesn't decrease, then the number would get bigger and bigger and bigger, but the power is decreasing. And because when the power decreases, let's say we have a number like 64. That has a lot of good roots. So 64 to the 1/2 power would be 8. 64 to the 1/3 power would be 4. 64 to the 1/6 power would be 2. And so on and so on and so on. But it would eventually reach 1, right? 64 to the 1/100th power. You're saying I need a number to times by itself 100 times and get 64. Well, then you're looking for a number that's just a little bit bigger than 1. Because if you have a number that's just barely bigger than 1, it times by itself a bunch of times before it actually starts to become something significant like 64. And so if you kind of extrapolate that out to infinity, then it's like, okay, we're basically at 1 at that point. Because 1 times 1 times 1 times 1 times 1 times 1. So at that point, we're basically at 1. And that's actually what happens even when the base is increasing as well. So n to the 1 over n, or any constant to the 1 over n, goes to 1 as it goes to infinity. So that's what's happening. And then, of course, so we can write infinity here, right? That would end up being basically 1 at that point. And that's important. We need to know, like, what are the boundaries. So it's not really bounded above. It's bounded above if it never goes above a certain point, and it doesn't ever go above 1.44 or 3 to the 1/3 power. But I think most teachers, most professors would not say that that's really a bounded above, because if you were to take the function backwards to like 0 and then negative values, you end up with like some weird stuff that happens for this particular function. But if you did, then it would end up being something else. Like you might end up with other values. So it's like, like I don't know if we would really say that it's bounded above. We would say it's definitely bounded below by 1. And it'll never actually reach 1, because 1 times itself an infinite number of times is still 1. So we would say it's bounded below by 1 because it's got that horizontal asymptote at 1, basically. So we would say it's bounded below by 1. And it would never actually reach that 1 value. And then monotone, increasing or decreasing. Monotone means it's doing the same thing over and over, like when somebody has a monotone voice. I don't even know how to sound. How do you sound monotone? I don't know. I guess you just do the same thing over and over. Am I monotone? Let me know if I'm monotone. Maybe I am monotone and I just don't realize it, because monotone people don't realize they're monotone. But let me know. But monotone would mean like you're doing the same thing over and over again. So if we're increasing all the time, we're monotone and increasing. If we're decreasing all the time, then we're monotone decreasing. If we're stagnant all the time, then we'd be monotone stagnant. There's not really an option for that. So we're decreasing. We're definitely decreasing. It's not a wave. It's not gonna take a while to level out. it's just leveling out. 1.44, 1.41, 1.38, 1.35 is decreasing pretty slowly, but it is decreasing, and it's always decreasing. So we would say monotone decreasing. Monotone decreasing. That actually pretty much concludes this video. But you know, if your teacher is looking for it to be worded a certain way, then just let me know in the comments, and I can talk about, you know, a couple. I have done this on a couple previous videos, so check out those as well, where like I'll talk about the couple different ways that you could say some of these answers. But I feel like it's too much to just keep doing it every video. So, anyways, just let me know if you feel like I'm missing anything here, or if you think I'm wrong. Um, and just let me know. And yeah, so I guess I'll catch you guys in the next video. Go check out my 5 math mistakes everyone makes and how to avoid them. It's on my website, Myers Mathematics. Link in the description below. Catch you all in the next video. Blessings, y'all.